Welcome back. In this next section with function transformations, we're going to be looking at parent functions and transformations. Transformations is a major theme of this entire year, and we're going to be looking at different types of functions. As we look at those types of functions, we'll also be ensuring that we know how to transform them and what effects those transformations have. So we'll see some of those parent functions now, so that when we investigate them a bit deeper later on, it'll be a bit easier, make things a bit simpler down the road. In order to really understand what's going on with those functions as we transform them, we need to know what's happening to their individual points, which we're kind of already familiar with, but also their domain and range, or any particular extra special features like endpoints or asymptotes. When we look at something like domain, it's worth noting that domain is just x values. That's a collection of x values that's valid for this function. That means that things like this 4 and this 9, which only affect y values, don't really matter. Not when we're talking about domain. What will matter is this 1/2 and this 3. So if we were to describe what's happening to this function when we transform it, just in terms of the horizontal changes, the ones that affect x, we have a horizontal stretch which means we multiply the x values by 2. And then we've got a shift to the right by 3. So when we have something like a original domain of -5 to 6, each of those changes by first being multiplied by 2 and then being added to 3. So if we take -5, multiply it by 2 and add 3, we get -7. -5 times 2 is -10, plus 3 is -7. Similarly, this ended had a right value of 6. We multiply that by 2 to get 12. We add 3 to get 15. One other thing worth noting here, this original domain went from -5 to 6 at a span of 11, right? There is a difference of 11 between the leftmost and the rightmost point. This one has a span of 22. The distance from the left to the right is 22. That's worth noting because our new one is twice the span as our old one. And that just ensures that we've applied something correctly because of this horizontal stretch by a factor of 2. So that left to right span should be twice as large. So hooray, huzzah, that's cool. I dare you to try these and see what happens. Some of them can be tricky. Well, it's just a few. But if you want, pause things now, and then I will proceed. way. Alright, I only see two things happening, all because of this negative 5. There's nothing else in the brackets. The negative causes a reflection over the y-axis, and the 5 causes a compression by a factor of 5. A reflection over the y-axis means we're going to multiply by negative 1. And a compression of factor 5 means we will be dividing by 5. And as we look at this, we'll note that I have better colors available. I like that blue. So something like negative infinity, let's write that elsewhere, gets multiplied by negative 1 to become positive infinity. Divide by 5, well, it's infinitely many, so when you divide by 5, it's still infinitely many. Something like 10, when we multiply by negative 1, becomes negative 10, and when we divide by 5, that becomes negative 2. So what originally was negative infinity to 10 is now positive infinity to negative 2. Just be careful on the phrasing. Typically when we state a span of numbers, we say it from least to greatest. You don't say I'm thinking of a number from 10 to 1. Maybe you're thinking of a number from 1 to 10. So as our proper notation is for domain and range, always go least to greatest. There it is. This one's asking for both domain and range. Looks like we got some space for that. So horizontal changes. We got compression by factor of 3. And we've got a leftward shift of 1. So when we check out our domain, which originally involved negative infinity and 12, divide that by 3, subtract 1, that's same. Divide this by 3, subtract 1, boom. Then we've also got our vertical changes. You're right, I do want that color. Boy. And vertically we've got a few. So there's a reflection. We've got a stretch. And we've got a shift. Oops. Let's look at what that does. What does that do to each component of this? Our range involved negative 6 and infinity. Multiply by negative 1. turns that into 6, turns this into negative infinity, stretching by a factor of 2, so our multiply by 2 turns this into 12, turns this into, oops, still negative infinity, and adding 5, we're there, and we're there. So for our new case, domain is negative infinity to 3. Ooh, I should be real careful with that bracket there. That should be round. And our range is from negative infinity to 17, I hope. If you want to take a break, if you want to pause the video, resume it at some other point in your life, another day, another hour, now might be a good time, because this particular section is a doozy. So now's a good point to take a break. We're going to look at some various parent functions. We'll kind of analyze them just a little bit. Maybe we'll do a little bit of graphing. But that's what we've got in store. So it's a doozy. Whoops, too far. Let's start with this parent function, y equals root x. Oops, you're right, there is more I need to add to this. If we look at the points on that particular function, when x is 0, y is 0. When x is 1, y is 1, the square root of 1 is 1. And another nice value is when x is 4, y is 2. This is pretty much the inverse of a parabola. I can draw that way nicer. Let's draw it like we care about it. So it's got a distinct endpoint right there, and then it goes on forever and ever that way. That's 1, that's 1. So two key points on this one are 0, 0, and 1, 1. If we look at the domain for this, domain goes from 0 to infinity. Starts at 0 and just goes on forever. And range actually is same. 0 to infinity. If we want to graph something like this, we can base it on this original parent graph and go from there. We note we're multiplying by 3, we're adding 1 just to the y values, nothing affecting x. So we have at it. What happens to those key points? The point 0, 0 turns into something. Nothing happens to the x values, they stay same, okay. Y values, they get multiplied by 3 and then we add 1. So 0 times 3 plus 1 is 1. What happens to the key point 1, 1? X values stay the same, there's again no changes in there. And then the y value of 1, we multiply by 3, we add 1. So 1 times 3 plus 1 is 4. If you want, you can even throw in another point there just to really get the guide for this. And then for the y value, 2 times 3 is 6, plus 1 is 7. We're good to go. There's probably more tick marks than I need. Yeah, sure, why not? Let's throw in more for good. Oop, that's uneven spacing. I can do better. We can essentially just plot those points at this point. So 0, 1 is on there. The point 1, 4, 2, 3, 4. And the point 4, 7, 4, 5, 6, 7 is there. And then we play connect the dots. Again, always taking care to connect these like we care about how the graph looks. All right, we're not just coming in there and being like, yeah, got it. So make sure it looks like you care about it. And of course, I'm just gonna label my scale here real quick. Quick, try this other one. Is that it? Oh, no. Yeah. Oh, we didn't say this thing's domain and range. Good point. Read this question fully. So domain, graphically, we can see that the x values didn't change. So, oops. We're going to go from 0 to infinity. The range, originally it was 0 to infinity, like that. We multiplied by 3, we added 1. So 0 times 3 plus 1 is 1. Infinity times 3 plus 1 is infinity. And we can see that matched in the graph here. And our lowest point is 1, and then it just keeps going up. But yes, give this a try, and then we continue. I'm jumping in. Zero, 0 turns into something. 1, 1 turns into something. 4, 2 turns into something. For our y values, we're just subtracting 2. So -2, -1, 0, okay? And our x values, we're multiplying by -1, and then we're adding 3. So -0 plus 3 is that. -1 plus 3. -4 plus 3 is that. Okay, so we're going into negative land here a little bit. Things we can kind of foresee, well, this horizontal flip is going to mean this thing points the other way, right? Where our original parent function goes that way, a horizontal flip means we're now going the other way instead. So that's worth anticipating while we make this graph, right? I don't really want to take this graph and say, well, going that way, might as well just prepare for that, because, like, whoops, that's going to be an issue at some point. Let's erase this, this, and this. Something's making noise around here and it's bothering me. That's fine. I'll survive. Anyways, let's prepare for this. Oh, this thing does go negative. I can do better. Of course, using a ruler is a Good idea. Don't forget. I'm going to put some little ticky marks, and we'll go for it. Yep, doing it now. All right, 0, 0 turns into 3, negative 2. And we've got 2, negative 1. And then negative 1, 0. That's the way the graph goes. Oakley dokes. Just going to label my scale now while I have a chance. And then I'm going to graph this thing. Oh man. But I can even get another key point. 1, 2, 3, 4, 5. Just for funsies. Ask yourself where I got this point from. My brain. But where did my brain get it from? What's the mathematical logic behind it? You say no one knows. Boop. Stating its domain and range. Domain-wise, we've flipped things, and then we've shifted right 3. And we can see there's a rightmost point here at 3, and that it continues towards infinity the other way. Negative infinity heading up to 3. And range-wise, we're as low as negative 2, and onward and upward forever. That took some time. But let's see if you can get the domain and range of each of these functions. Now again, we're looking at the original domain and range, which were both just everything non-negative. So based on that, based on what happens in each case, state what happens. Where's my trusted, yes, blue. That'll work. So for domain, which would go from, again, 0 to infinity. In this case, horizontally, we're just subtracting 5. And then range-wise, vertically, we're multiplying by half and then subtracting 3. 0 times half minus 3 is negative 3. Infinity times half minus 3 is still 3. Boom, done. Yeah, there's space for that right over there. Next up, again, domain. In terms of x, we're just squishing by a factor of 2, so dividing by 2. 0 divided by 2 is 0. Infinity divided by 2 is infinity. Range-wise, we're multiplying by negative 4. We're adding 5. So when we multiply 0 by negative 4 and then add 5, you're going to have to erase what I'm about to put down if you're writing down at the same speed. Just letting you know. That turns into that. And then infinity times negative 4 is negative infinity, plus 5 is still negative infinity. So we've got this, like, whoa! That's the wrong order. So just make sure that you actually write that opposite like. So from negative infinity to 5. Where is it? And this last one. Ba-da-ba-ba-ba. Domain. We're multiplying by 2/3, and then we're adding 9. 0 times 2/3 is 0, plus 9 is 9. Infinity times 2/3 is infinity, plus 9 is infinity. Range-wise, we're just multiplying by 3. Did I say multiplying by 2/3 for that one? That should be dividing by 2/3. Didn't change our answer. So range-wise, we're just straight up multiplying by 3. There's no uppy downy shift. 0 times 3 is 0. Infinity times 3 is infinity. That one is done. Ooh, exponential functions. Wowee. Those are pretty fun. There's infinitely many exponential functions, all depending on what base we choose. This one is y equals 2 to the x. In general, they'll have the form y equals a to the x. But just so we can get an initial feel for them, we'll talk specifically about y equals 2 to the power of x. It's not a bad function overall. Keeps things positive anyways. The best jokes. Anyways. When x is equal to, well, it's a certified thick marker. When x is equal to 0, y is 2 to the power of 0, which is 1. When x is equal to 1, y is equal to 2 to the power of 1, which is 2. If you want, you can throw another one in there. When x is equal to 2, y is 2 to the power of 2, which is 4. If you really want another one in there, what happens when x is negative 1? Well, then 2 to the power of negative 1 is half. This function does some interesting things. That's y, that's x. Hooray, huzzah. So let's draw the stirf out. Where my purple at? That's necessary. Sure. Oops. Whoa. Hold on there, friendo. Doing space, bro. Okay, that's fine. And sure. I'm just giving some wide space on this one. Something gnarly is about to happen. So we've got the point 0, 1. We've got the point 1, 2. We've got the point 2, 4. And it looks almost like, hey, maybe this is going to be kind of like a parabola. Our next point is on the left side is 1, or negative 1, 1/2. And if you really analyze it, if x was negative 2, we'd be looking at y being 1/4. If x was negative 3, we're like at 1/8. And really, these are the only critical, or well, key points. What's necessary to note is it explodes up this side, but on the other end, it just gets just closer and closer and closer to 0. It never quite reaches 0 because even if we had 2 to the power of negative 1,000, that's really just talking about 1 over 2 to the power of 1,000. And there's always this 1 on top, which means this is never equal to 0. It gets close. Like 1 out of 2 to the power of 1,000 is ridiculously close to 0. It's just not quite there. Like it tried. Nice try. So, even though we connect these dots, la 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 la, la 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 la, la la, so we have an asymptote. Right along this axis is a guiding line for this function to follow. So as it goes further and further to the left over there, it tries to follow this guiding line. It gets infinitely close to it. Doesn't ever quite meet it. This line in this case is the same thing as the x-axis. Its equation is y equals 0. Always make sure you label your asymptotes. Draw them and label them. So any exponential function you have, you'll have to provide that. Domain and range of this thing. Did I use a different color for domain and range? I don't even, it's been so long. No, I just went same color the whole throughout. Okay, so I guess we're back to purple. So domain goes from negative infinity to infinity. That'll be nice when we're talking about what its domain is for its transformations. And range-wise, we go as low as 0, but... Oh, get right out of here. We go as low as 0, but don't ever quite meet it, so that's a round bracket at 0. Did it actually just modify my bracket? And we go all the way up to positive infinity. And there's an asymptote, which we noted over here. Let's state it again. Y equals 0. So let's graph some of these. Give it a try. Use transformations to your benefit. And see what happens. Black. I like exponential functions because they look cool. Whoa, I'm just wondering right now, did I ever indicate my scale up there? Oh no, what a failure. That's 1, that can be 2. All right, now we're in business. Let's see what happens to some of these points. Like, what are our key points? Oh, 0, 1, and 1, 2, sure. So 0, 1 turns into something, the point 1, 2 turns into something, the point 2, 4 turns into something. What happens to all of these? Looks like nothing is happening to our x values. But our y values we're multiplying by 3 and subtracting 1. So 1 times 3 is 3, minus 1 is 2. 2 times 3 minus 1 is 5. And then 4 times 3 minus 1 is 11. So those are the key points we need on this thing. We need to make sure it goes at least up to 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Sure. Oh, those last ones are lazy. That's better. But we should also note that our asymptote changes. So our asymptote was y equals 0, but our y values are changing. We're multiplying by 3 and subtracting 1. Boop. So 0 times 3 minus 1 gives us that. At that point, we can start plotting these things. We can add our dotted line for our asymptote. Which we will, of course, label nicely. We can also take this and just line it up. Gorgeous, gorgeous. All right, let's plot these points. 0, 2. 1, 5, 3, 4, 5. Noise. And what is this? 11, 5, 6, 7, 8, 9, 10, 11. Gee, I wonder if when x is -1, this thing would be positive or negative. I guess positive. Why? I don't know. Nice little mysteries. That's worth investigating if you want to investigate it. Or you can just take my word for it for now. But it would be a quick investigation if you wanted to do it. Just table of values. See what happens. Boom. Boom. Domain of this thing, unchanged. Range of this thing, now we're going as low as -1 because of that subtraction by 1. Let's try this one. Ooh, we got a vertical flip. So instead of this thing looking like this, watch out, it gonna look like this because of that vertical flip you do. So heads up, it's there. You're right, I did not indicate my scale on that previous one, and I really need to do that. I'll do that now. This can be 1, that's thick. This can be 1, this can be 2. And now I've got all the marks. Y, X. Things happen to our key points, of course. 0, 1 turns into something. 1, 2 turns into something. Even 2, 4 turns into something. X values, we subtract 4. Y values, we multiply by -1. Yeah. So that's that. Mistakes were made. We're going to be kind of like that, he thinks. Yep. All right. So we'll plot our points. That one. And that one. You're right. You know what? I don't like the scale I chose. I'm going to double up. All right. -4, -1, -3, -2, -2, -4. Where's our asymptote? What happened to y = 0? Well, all we did to the y values is multiply by -1, so it's still y = 0. We'll draw that in. Blah, 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 blah. We'll label it, and then we'll play our connect the dots game. What a great game. Domain-wise, Well, still going negative infinity to infinity. Range-wise, well, it used to be 0 to infinity, but we flipped that upside down. So now it's negative infinity all the way up to 0. So for all of these, we've noticed that domain is not changing. Boom diada, boom diada, boom diada, boom diada. But stuff happens to the range. So that's really what we're concerned about here. In this case, we just add 3. So we go from 3 to infinity. In this case, we multiply by negative 5. So our range of 0 to infinity turns into 0 and negative infinity. Don't forget the order. So negative infinity to 0. And multiplying by 4, subtracting 7 gives us that. If you need another break, now would be a good chance to do so. Now we're getting into sinusoidal functions. So this is based on the graph of y equals sine x. It's an interesting one. If you ever want to see what that looks like, don't forget you can use Desmos. Functions. Sine of x. Ooh, interesting. Let's put this thing into degrees. And I'm just going to play around with my axes. So this is what it looks like. You're right, I can zoom out a bit more. So this is what the sine wave looks like. Look at that. Oopsie daisy. At 0 degrees, sine of x is 0. Over here, at when x is 90 degrees, sine of 90 is 1. Sine of 180 is 0. Sine of 270 is negative 1. Sine of 360 is 0. So that's what we're playing with in this case. Those are essentially our key points here. Joomph. Oh, come on. Joomph. So when we draw this thing, I wanted a thicker line. We've got key things happening at Oish. At 90, at 180, at 270, at, you know what? Do better. I will. Yeah, that's what I want. At 90, at 180, at 270, at 360, things will happen. They'll happen exactly as we just saw them. So there's y, here's x. Our key points are 0, 0. Wait. When x is 90 degrees, sine of x is 1. When x is 180 degrees, we're back to 0. When we're at 270 degrees, we're at negative 1. We're at 360 degrees, we're back at 0. So this one's a bit of a doozy. The nice thing is that it is just alternating between positive 1 and negative 1. So our points form a cycle. So here's what it initially looks like. It does go on forever ever. While we make this curve look real beautiful. Oh, this is just gorgeous. If I had to tell you what my favorite parent functions are, it'd easily be sinusoidal functions. I take great pride in modifying my sinusoidal functions. Alright, there's that. The domain and range of this thing. Domain's another nice domain. It goes on forever. And range from -1 to +1. Yeah, we'll put this in the right spot, like right there. So, let's dive right in and graph a couple of these. Okay, sounds great. Let's draw some axes. I label all my scale aside. There we go. Let's get some axes in here. Boom. And boom. And let's go for it. Let's see what happens to our key points. So we had 0, 0. We had 180. And, oh, we had 90, fool. And 1. We had 180 and 0. 270 and -1. We had 360 and 0. They all turn into something. No horizontal changes here. Oakley dokes. So we're still dealing with those. And then vertical changes, multiply by 2, add 1. So 0 times 2 plus 1, boom. 1 times 2 plus 1 is that 0 times 2 plus 1. -1 times 2 plus 1. And 0 times 2 plus 1. Whammy. And now let's plot all this on here somewhere. I need to make sure I go as high as 3 and as low as -1. So as long as we have tick marks for that, we're all good. And then for 90, 180, 270, 360. Let's plot them. 0, 1, 90 and 3, 180 and 1, 270 and -1. Oh, who wrote this? Let's back out of 1. That. We play connect the dots. It looks beautiful, just like us. Ooh. And of course, I always remember to label my axes. That's that. You can try the next one if you want. It's a little bit of a doozy. Not really a doozy, but try it. See what happens. This video is long. If you're doing this in one shot, I'm a little impressed. I am hearing audio. Is that a computer? But it says the volume's off. Well, life's tough. I'm tougher. Only our x values change here. We divide by 2, we add 90. 0 divided by 2 plus 90 is 90. 90 divided by 2 plus 90 is 135. 180 divided by 2 plus 90 is, ooh, it's 180. 270 divided by 2 is, where are we at? That's like 135 plus 90 is 225. Wait, how do you spell? There. 360 divided by 2 is 180 plus 90 is 270. Those are the points we're going to plot on here. How do we choose a scale for this? It looks like these are all 45 apart. So I'm just going to make this thing go up in 45s. So this will be 45, 90, 135, 180, 225, 270. There's X, there's Y. So we have the point 90. Oh, where's my purple? 0. I need my 1 and negative 1. 135, 1, 180, 0, 225, negative 1, 270, 0. We play connect the dots. And I finished labeling my axes, of course. This thing is done. That was a doozy. So, oh, you're right. We should state domain and range for these. Why not? Domain, unceasingly infinite. Range, this one goes from negative 1 to 3. And that's because we took our original ones. Our original one was negative 1 to 1. We multiplied by 2, added 1. Got us there. This one, we didn't change the y values at all. So everything just stayed full on consistent. So let's take the domain and range of these. Domain for all of them, super infinite. It's huge. The range though, so noting our original range, goes from negative 1 to 1. We are going to, in this case, multiply by 3 and subtract 1. Which for this one, negative 1 times 3 is negative 3, minus 1 is negative 4. 1 times 3 is whatever that number is. 3 minus 1 is 2. This next one, the flippity-doo doesn't change anything really. It turns this into 1, turns that into negative 1. But that's just the same thing. Negative 1 to 1. So that doesn't concern us. The only thing that concerns us is really this plus 5 then. Which means that we're going from 4 to 6. And ooh, times half, and then subtract 3. So negative 0.5 minus, negative 0.5 minus 3 is negative 3.5. And then positive 0.5 minus 3 is negative 2.5. That's that one. Think rational functions, the last one we're looking at. Let's just do a quick scan here. Yup. So we're getting there. Rational function, the base function is y equals 1 over x. This is another one with asymptotes involved, mainly because you can't divide by 0, and 1 divided by anything will never be 0. So we've got two particular key points in this one. That's when x is 1 and when x is negative 1. But we do also have asymptotes. So when x is 1, y is 1 over 1, which is 1. When x is negative 1, y is 1 over negative 1, which is negative 1. Absolutely gorgeous. We plot this thing. Boom, boom, there's those. But what happens with the relation y equals 1 over x, oh yeah, let's just do this the nice way. One divided by x, oh let's zoom normally there, is all this stuff. So it curves towards the axis on every single spot. On the right side, we're staying positive. On the left side, we're completely negative. But curving towards the asymptotes. As x gets really high, 1 divided by really high numbers gets close to 0. And because of the reciprocal relationship, as y gets really high, x gets really close to 0. So they work in tandem with one another. So we have two asymptotes. One is this vertical asymptote. That's right on the y-axis. That vertical asymptote has the equation x equals 0. And then we've got this horizontal asymptote. That's right on the x-axis. And that is the equation y equals 0. Get out of there. So for domain and range, there's a variety of ways to state this. I would say the easiest way to state the domain is, let's go really nice notation. You can say it's all the x's, but x is just never 0. Otherwise, it's all real numbers. The range is actually same. It's all the y's, just that y can't be equal to 0. Otherwise, other than that, y can be any real number. Our asymptotes are at y equals 0 and x equals 0. So those are the features we have to pay attention to when we transform this. Whoa, hey, yo, I don't want other apps. Let's figure out what happens to our key points. Let's graph these things. We had a key point at 1, 1. We had a key point at negative 1, negative 1. We also had an asymptote at y equals 0. We had an asymptote at x equals 0. Where did all of those things go? Here I just see translations. I see an upward shift of 2, and I see a rightward shift of 4. So a rightward shift of 4 means any x values we add 4 to. So add 4. Not adding 4 to this, because that's not an x value. Only the x values. And then to the y values, we're adding 2. So over here, y was 0 for an asymptote. Now y is equal to 2. You can handle all the rest of this in whatever order your heart desires. Oh, that's tiny. Personally, when it comes to rationals, I have a tendency to prefer to place all my asymptotes first, and then I go from there. Don't mind me as I just mark my scale. Someone should remind me to just put these axes on here for everyone already ready for future years. Anyways, asymptote at x equals 4. Boom, 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 boom. And asymptote at y equals 2. Boom, 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 ba-cha. Boom, 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 ba-cha. Then we plot our points at 5, 3, and 3, 1. What do? We trend towards asymptotes. Now these don't, for the rational function, they don't cross the asymptotes, so we're not going this way or anything. So this guide's this way, this way. That's the shape it's going to take. You don't have to necessarily memorize the shape, but honestly, it might be your best way to go. Quick recall. I mean, still understand why it does that, why it takes on that shape, but quick recall can be extremely useful when you're finishing this thing off. Right? You can understand why 2 plus 2 is 4, but you'll want to have the quick recall that 2 plus 2 is 4, boom, move on. That one is graphed, except for the fact that it's missing a scale. Alright, I've indicated my scale. Last one to graph. We are getting so close to the end. Soon I'll be able to have a glass of water and stop talking. Maybe even have a nap. Dreams. As in having a nap is my dream. Not that I'm going to have dreams. I probably will. Right. Oh, there's only vertical changes here. That's interesting. Cute. 1, 1 turns into something. -1, -1 turns into something. Y equals 0, x equals 0. Those are all the things that we have to modify. Whoop, let's rewind. Domain and range of this thing. Let's just short form this. X can't be 4. Range. Y cannot be 2. Alright, moving on. What happens to this thing-a-ling? Only vertical changes. We're vertically stretching by a factor of 3. We are subtracting 1, so going down 1. So our x value stays same. Y times 3 minus 1. Boom. X value stays the same. Y, we are multiplying by 3. We are subtracting 1. Y values, we are multiplying by 3. We are subtracting 1. And then x values, again, we aren't changing. That stays same. Let's get ready to plot this thing. The thing when it comes to rational functions, I like to really make sure that I can show how it reaches the axis. I want to show that trend of it going toward the asymptotes. So you'll notice I've kind of condensed things for y values here, for my y scale, just so I can really exaggerate that effect. I've got asymptotes, where y is -1. x is 0. And I've got points. I've got the point 1, 2. I've got the point -1, -4. And from there, trend towards the asymptotes. Ooh, where does it cross it actually? I wonder about that. Oh, at 3, hey? That's good to know. Just curious. How did I get that? I don't even know. But if you want to compute the x-intercept, go for it. You have the ability to find it. Just remember, ask yourself what an x-intercept is, what it means for the y value, and go from there. You'll be formally shown that business, perhaps, when we actually study these types of functions later. All right, domain and range of this thing. Basically, in this case, x still just doesn't equal 0 in range. Y does not equal -1. So these are kind of nice because there's not really a whole lot to have to pay attention to. They're basically infinite, except for that one thing that they can't be. In this case, because of this leftward shift of 3, x can't be -3. We also know that's a non-permissible value for this expression anyways. Right? We can't make that denominator 3. That's unheard of. Range is just straight up. Oops, try it again. Y cannot be 4. We were at 0, we can't be 0, but now we've gone up by 4. So you really speed through the rest of these. Domain, x can't be +1. Range, there was no up-down shift, so we're still looking at that. And finally, we went left 8, so whoa. So x will not be -8, and we went down 14, so this asymptote went down 14 as well. There's no textbook practice work for this one. Boy, has it been a doozy. Thank you for bearing with me through it. It's like 2 hours past my bedtime, so getting a little worn down. But that is this one complete. Our next lesson will be to finish off topic 1. So we're getting close to the end. Thank you for paying attention to this lesson. I hope you found it valuable. And if you have any questions, comments, concerns, don't forget to ask me, either in class or via Teams. I'm going to have a glass of water, and I'm going to have an 8-hour nap. Peace in and around the streets.